Moving on from electric fields, our next topic is magnetism and magnetic fields. Disclaimer right off the bat, this first chunk is going to be review of grade 11. We're coming from different places. Some people learned in school, some people learned online, some people learned hybrid. So we're going to review the grade 11 stuff. Bottom line is magnetism's just a little bit more complicated. So we're going to review this first part of the document I shared with my grade 11s. So I've just beefed up a grade 11 document. I'll talk you through it, and we're going to learn about magnetism and magnetic fields. If you've peeked, you know that this is a long document, 19 pages or something ridiculous. It's got 16 pages. It's got a lot of diagrams, so it's not as dense as a 16-page document might scare you into thinking it is. I'm going to chunk these videos. I'll talk you through the intro part and then next video to get through the next part. It really is what we did in grade 11, left-hand, right-hand rules. I'm going to talk you through the logic. I'm going to remind you of the left-hand, right-hand rules, and in grade 12 we add an equation. So it's just a little bit of addition. The note's not as overwhelming as it may first make you think when you see it's 16 pages. Here we go. Reviewing gravity and gravitational fields. We talked about those. They're the simplest. Mass creates a gravitational field. There's only one kind of mass. Even if we talk about weird things like antimatter or dark matter, it's still just mass. And usually once you've got a mass, it doesn't change. Like the mass of the Earth is that 5.97 number, it's not changing. And then we could say like if we have two masses, they create their own gravitational field. If the two masses are close enough together that their gravitational fields overlap, that's what triggers the gravitational force and stores gravitational energy. If we bump it up a little bit and switch to talk about electricity, they're just a little bit more complicated. It's the same idea. A property creates a field. In this case, the property is charge. But now we've got two kinds of charge, and we named them positive and negative. And electrons are wee tiny light things that are free to move, so the amount of charge can change. Classic example, and it'll pay off when we talk about magnetism. There's a demo of it online here, but if you were to rub a balloon on a sweater and stick the balloon to a wall. I'm typing it to match the simulation. It's a grade 9 electrostatics, which way the electrons are going to go. The way that it's typed, programmed, the electrons in that simulation leave the sweater and go onto the balloon. If you want, pause and go play with that. What that means is that the balloon becomes negatively charged and the sweater becomes positive. If we take the negative balloon and bring it close to the wall, it induces or it creates a charge in the chunk of the wall behind the balloon. The wall was neutral, but the influence of this charged balloon makes the wall become positive. Since opposites attract, the balloon sticks to the wall. That's a weird thing in electricity that we didn't see with gravity. Now, bumping it up one more level, and this is actually the topic of the day, magnetism. Magnetism is just a little bit more complicated again. There's two different models to explain what creates magnetism. For gravity, it was easy. Mass, that's what creates gravity. For electricity, easy. Charge, that's what creates electricity. There's two kinds of charge, but those charges create electricity. For magnetism, it's a little bit weirder. What is it about a material that makes that material magnetic? We'll come back to that in a sec. Once we're okay with the idea that there's magnets, each magnet has, they called them poles, named after their most common application way back when, which was navigation, which was a geography thing. So they called them the north-seeking pole and the south-seeking pole. What's weird about a magnet, what's different than electricity, is you can't have just a north pole or just a south pole. Every magnet in the universe has both poles, a north-seeking and a south-seeking. If you wanted to get clever, if you had a nice bar magnet and cut it in half, you wouldn't get one half that was north and one half that was south. You just get two smaller bar magnets, and each bar magnet would have a north and a south. And the last point, similar to electricity, whether an object is magnetic or not can change. Some objects are always magnetic. Those are what we call permanent magnets. Those are what you've got stuck to the fridge at home. Back in the day, you would have had magnets stuck to the inside of your locker. Those are permanent magnets. Then there are other objects, kind of like the wall when we brought the balloon close by, that become magnetic when a magnet is close by. That's like the metal of your fridge. Your fridge isn't a magnet. If you took a paper clip and held it against your fridge, it's not going to stick. That means your fridge is not magnetic. But if you bring a permanent magnet close to the fridge, that induces magnetism in the metal of the fridge, kind of like the charged balloon induced charge in the wall. So the fridge becomes a little bit magnetic close to that permanent magnet, so your permanent magnet can stick to the fridge. The balloon induced a charge, the permanent magnet can induce magnetism. What's weird about the fridge? Well, it's kind of like the wall. When you take the permanent magnet off the fridge goes back to being non-magnetic. So we've got things like magnets that are always magnetic, things like your fridge that are magnetic when a permanent magnet's close by. And I didn't type it, then we've got other things like wood, plastic, things that aren't magnetic and don't become magnetic. So whatever makes things magnetic has got to be a little bit weirder. It's not just not like charge where you just gain electrons or lose electrons. There's something else going on here. The model, what makes magnets? There's actually two models that explain what makes an object magnetic. There's a cool, more complicated model that's atomic theory and outer shell electrons. I learned it a long time ago and I don't remember the details very well. That's the model that you're going to learn in chemistry class. So Miss Beaton, Mr. Montgomery, Snatty are going to talk about outer valence shell, blah, blah, blah. And there's an explanation within that about why some things are magnetic and why some are permanent magnetic and why some are those ones that flip-flop. We don't need that model. So we can get by with the simpler model. The simpler model is related to particle theory that you learned way, way, way back in like grade 9 science. We are going to say that all matter is made of particles. And what we're going to add to our particle theory is that all those particles themselves kind of behave like teeny tiny bar magnets. If we've got a material and the teeny tiny bar magnets are pointing all over the place in random directions, then those tiny magnets cancel each other out and that bigger object is not a magnet. That's what's going on in this little image. This would be like a piece of wood or something. In the piece of wood, the wood's made up of particles. The particles are behaving like tiny magnets, but the magnets are pointing all over the place. Like up in this top left corner, the magnets are pointing down. But over here, they're pointing up. They're going to kind of cancel each other out. Here, the magnets are pointing to the left. Over here, they're pointing to the right. They're going to cancel each other out. As opposed to an object where the dipoles agree or line up in the same direction. If we've got a material and the dipoles point in the same direction, then they don't cancel each other out, then the bigger object is going to be magnetic. Now, vocabulary-wise, sometimes they call these little zones that they've labeled in here, sometimes they call those domains. They use the word dipoles because there's two poles to a magnet, the north pole and the south pole. So often people say if the dipoles are lined up, then the dipoles in the domains, if they're lined up, then the object is magnetic. But if those dipoles are randomly aligned or not lined up, then the object is not magnetic. That is the theory we're going to use for why objects are magnetic or not magnetic. It works to explain it. In a material like wood or plastic that aren't magnetic and never become magnetic, these domains are locked in and these little tiny magnets never ever move. In like the metal of your fridge, if you brought a permanent magnet close by, then all of these things would sort of pivot around so that they do line up. So maybe they change that they're all pointing up. Then this thing would act like a permanent magnet because they're all pointing the same way. But then when you remove the permanent magnet, all these things go back to their original orientation and the thing stops being a magnet. So it's a simple theory, but it works to explain what we see in the real world. That's really all we need a theory to do. Moving along, I've said all this out loud, so you read through that. I'm going to skip over that. The last little piece I want to go, and then we'll pause this one. Again, it's something that you should have seen in grade 11. Make sure you read that stuff first. If an object's magnetic, so if it's got these dipoles that are lined up, we say it's surrounded by an invisible magnetic field. Magnetic field is like the diagram of the wind that I showed you a few lessons ago, a field of arrows that explain the direction and the size. There was a rule to the gravity fields. The gravity fields pointed in the direction an imaginary mass was forced, pushed, or pulled. There is a rule to electric fields. the electric field of a charged object is the direction an imaginary positive will get pushed or pulled. Similarly, there's a rule for magnetic fields. The rule for magnetic fields is they're a field of arrows that point in the direction that the north pole of a small compass would point. So, classic, let's say we had a bar magnet. So picture down here, bar magnet, north pole up here, south pole down here. That's our bar magnet. If we were to put a wee little compass, so go over to the dollar store, buy yourself a wee little compass. If we put the compass right here, then the north pole of the compass is going to repel away from that north pole of the permanent magnet and point kind of that way on a funny angle. If we put it over here, it's going to point upward on that funny angle. If we put it down here, it's going to get pulled in, attract to the south over there. So if I used to try and do this as an experiment, I'd give kids a bar magnet, I'd give kids a bunch of little tiny dollar store magnets and see if they could draw the field lines based on what the dollar store compass was doing. It ended up being a disaster because the dollar store compasses would fall apart and it just wasn't worth the aggravation. If we could do it, we get this cool, what I'm going to call the classic butterfly shape. The magnetic field of a bar magnet kind of looks like butterfly. We got these wings out the side, looping down and into the south. I don't know, do butterflies have antennas, but lines coming out the top, lines pulling into the bottom. That is the magnetic field of a bar magnet. Things to notice are the magnetic field lines always point out of the North Pole and into the South Pole. If you were walking down the street and found something, a chunk of metal, and if you held a compass close to it, and when you held the compass close to it, the North Pole, you got field lines that did this, pointed out of that end, and field lines that drew into that end. That thing that you found, because it's influencing a compass, it must be a magnet. Because the lines are pointing out of the right, let's say that's what it did, then that right end must be the North Pole. Since they're getting drawn into the left end must be the South Pole. I know that whenever we have magnetic field lines, they always point out of the North Pole and into the South Pole. Kind of like we did with that wind picture way back when, the density, how close the lines are together, is a measure of how powerful the field is. If we just do single arrows, how long the arrows are, but that explains part of it, but also how densely they're packed together. Notice that there's not a lot of field lines at the side of a bar magnet. If you've ever played with a bar magnet, you know that things don't stick to the side of them, things stick to the ends. That's kind of the field lines are showing that because the field lines are kind of bunched together by the ends, and there's not many field lines by the sides. That is a little summary here. Read through that. That is my little blurb about magnetism, why some materials act like a magnet, and importantly, field lines always pointing out of the north and into the south. I'm going to pause this video and I'm going to start a new one. Before you watch the new video, it's all about electromagnetism. Watch this little demo first.